It's our pleasure today to welcome Dr. Rengin Gok from Lawrence Livermore National Lab. And she, as you know, she's working on the very important subject for our country. And there is and presenting project results on the seismic hazard assessment for generally Caucasus, but we believe that today we will hear much more about the Georgia. So thank you for coming and thank you for this presentation. Thank you for your efforts.
Thank you very much for hosting us in this beautiful conference room. It's my first time, I think, being in such a beautiful room with so exotic and architectural design. Thanks to the Ministry of Education, Science, Culture and Sports for hosting us here again. We're very excited to present the results of our study in the country for starting 2015, but actually our collaboration goes back to 2001, I may say, because even before my time, before I started working at the lab, Lawrence Livermore National Laboratory came here and helped improving seismic network and improving capacity of the country in monitoring earthquakes. So my name is Rengin Gok. I am a seismologist and also program manager of Seismic Cooperation Program at Lawrence Livermore National Laboratory. My colleague, Taya Godaladze, she is the director of the Institute of Earth Sciences at Ilyich State University. This presentation is the product of our collaborative effort in building the catalog in the country, in Georgia. Next one. So I just wanted to give to the audience a kind of very short overview about where I come from, what kind of research and developments are being done. Very short, there's 8,000 people in a square mile place that you saw the picture of. But very exciting scientific developments are always being done. That's what we are after in Livermore. We have the most powerful supercomputers in the world, and we are actually ranked 3 as the fastest computer of the world. And we have the world's largest and most energetic laser facility. We have the ultra-sensitive isotope measurements. It's not only seismology, very many different disciplines, and very exciting science being developed. Next one. And I like to kind of highlight my group a little bit because when I come and present myself here, most of the work I have is actually is kind of combined effort of my group of people, because everyone in the group has specific specialty, expertise, and they contribute into my overall they contribute to my overall scientific development wherever I go, whatever I do. So I just wanted to give like 3 exciting topics we have been working on. One of my colleagues are working on improving location algorithms using Bayesian method, and look at the error ellipses, because earthquakes are always shown in dots, but they come always with the errors that are never very clear to the regular audience, but we know it. We know how and well they are defined. And also the global tomography at the lab, we have been using the worldwide networks and other deployments to come up with the world Earth model that goes down to the deep core. And on the side, we're developing with very fast high performance computing, ground motion simulation analysis, like how can we predict a big earthquake if we don't have any data from the past, if we don't know the strong motion, or if it is likely to have a rupture. This is Bay Area where I live. There is a fault, and this is the scenario. If you visit one day California, we have the exhibition at the Academy of Science, California Academy of Sciences at the Golden Gate Park. They have the show for the ground motion simulation that are created at the lab by us. Next one. So I want to also touch a little bit about what seismic cooperation program is. I've been managing this program since 2009, but this goes back to 1990s. So we have several goals, but basically we deploy stations, we do joint data analysis, we try to enhance seismic models and location analysis, and also really looking for strengthening international capabilities and transparency throughout the region. That, for example, for the earthquakes, it's really important to share data, and the earthquakes don't have boundaries. If you want to do a better job with the earthquakes, it's very important to connect the power, basically. And I currently have 14 countries engagements with in the Middle East, Central Asia, and the Caucasus. This is one of the projects that I was managing. So, why we're doing PSH in Georgia? And this is probably most of you have this in your mind. I just wanted to put that slide to make it clear why we came up with this idea. Why? Because earthquake catalog is the backbone of any PSHA study. If you want to have good results, your catalog must be very good. And with that, we saw a potential to significantly improve the number of events in the catalog using former Soviet monitoring network data. And that goes back to 1955, because it was a really beautiful network, many stations, but the records were all written on the paper. So we saw the potential to improve this by also combining bulletins from neighboring countries such as Azerbaijan and Armenia. That helped us improving location accuracies, also paved the road for future collaboration for data exchange between the countries. The other contribution that we think will be really important for the catalog is the ability to measure directly MWs, moment magnitudes, which you will see in the future slides, from small events to improve the magnitude relationships. So, also, we will continue this process in Armenia and Azerbaijan after we are complete here in Georgia. Next one. So, we have been busy for the last 3 years, a lot of workshops. Institute of Earth Science created this beautiful software to combine the data recorded from other countries. And that they can actually, even from their country, look at their bulletin, enter the information, and calculate the location themselves. So they created this to be open to the participants, and we had 6 regional workshops that I remember, and this is one of them in Kazbegi. We had picked many different places, but we worked really hard to get this results really merged and come up with a meaningful catalog. Next one. So this is, So this is a nice figure, kind of shows in color code which countries contributed with which arrivals. Turkey was part of it at some point when the catalog was being developed, because Turkey has their own PSHA team, PSHA group that they're able to get themselves into the modern building code standards, but they helped us to improve our catalogs in the region that are close to the border. So that was very important. Next one. We, as seismologists, because my heart is always in the data, how accurate and correct this data is being implemented, I always look at how accurate my earthquake locations are. And this is the figure I got from my colleague Isvan Bondar, who was here to actually help us improving catalogs too. So if you look at this picture, the figure on the right, the stations are triangles, and the earthquake is in the middle, okay? And the blue lines are showing you where the azimuthal gap is. This is the term we use a lot. Gap, meaning if you have a missing angle from any station, then your location will be biased, earthquake location. And we have a term also introduced now, so it's called a secondary gap. If you have one station in between, it doesn't really help too much. So we want to know even what is the secondary gap too. So if you look at on the left, look at the plot of secondary gap. If you have more than 180 degrees, you're in trouble. Your locations can be as long as 20 kilometers. And it goes up to 40, 50 kilometers, which is major because literally the source zone changes. Next one. So this is the problem that I want everybody to keep in mind. The location problem is really need to be considered carefully, and when you use the data from it, you need to look at the error ellipses and error values. So what we did, I mentioned about this former Soviet catalog in the Caucasus, that there was room full of papers written form, and we took everything. Actually, Thea and her team, they took everything, they digitized it. This wasn't even funded by us. This portion was done by them just during their regular monitoring performance. But what we did, we made sure these events are digitally recorded and shared with other countries, and other countries also contributed from their own bulletins. So now let's look at this map. So those are earthquake locations. Next one. So earthquakes don't locate like that. It cannot be on the grids. It cannot be on the regular grid lines. There is something wrong with it, because when you look at the map and when you see the lines, it means that there is a problem with the location. Next one. So we took this data. Actually, this goes back to even earlier years. When I saw this, there were 80,000 events, and I talked to Thea. I said, Thea, we need to do something with this because this data is very good, and let's first look at if we can get a good velocity model from this, one-dimensional velocity model that represents the country, which is also used to locate the earthquakes. We did that. This goes back to earlier years. From 80,000 events, imagine how bad it was. Only 3,000 was selected. It's not only it's bad, sometimes it's written wrong way, sometimes it's not maybe digitized in the right way. There are lots of different problems, but the overall picture shows that with all these earthquakes very well distributed and stations recorded them, we can come up with a very nice reference model of the region. Next one. So after combining everything, relocating with the algorithm that we used, iLoc, and now we're going to try with BaseLoc. This is how the catalog looks like. To me, I always tell to kids when I teach them at the science fairs, like, look at the earthquake catalog and squint your eyes and look if you see something meaningful. If you cannot do it, then it means there's a problem. So we can do the same thing, so this is a very active region, unfortunately. But the good news is I want to make this point. Seismology is very new science. Our information about Earth goes back to instrumental period, goes back to only 100 years, which is not enough, because earthquakes occur every maybe 500 years. Every 200 years, every 150 years. So we don't have enough information. We are trying to barely get the sense of what we can get the most from what we have currently. So the goal is to get the best out of it. So I'm sure if you put thousands of stations in the region, you will have much better map. But with the current status, this is the best map of catalog on events that we came up with. Next one. So in the earthquake location, in the earthquake catalog for PSHE, the other important parameter is magnitude. Because magnitudes, which we will show in the future slides, magnitudes really identify the hazard levels, because if the seismicity happens with the high magnitudes, then you have higher hazard. Very simple. And that's why how you convert the magnitudes from the old catalog or new catalog, whatever you use, to the basic accepted value is very important. That's something we were after. And we carefully analyzed this issue and looked at the intervals of years, which magnitudes we should be using to bring everything to the one level. And this is like the hierarchy we use. And K class is the famous Soviet type, and I'm sure many of you know, magnitude scale. Next one. So we took that. I want to show this figure is a little bit carefully needed to be examined. So here you see the magnitude relationship in 3 slides. So one shows on the left K class with the magnitude that I calculated for using Coda calibration technique, which I will show. And the other one is using MB to MW conversion. And the third one, these are just examples, I'm not showing everything. Third one is the ML to MW. So K-class magnitude actually performed quite well. That means that when we compared with our direct magnitudes, you see the scatter on the left is not as big as I personally expected. MB was kind of surprising because we wanted to use GEM relationship first, because MBs are usually international centers report MBs, not local networks. So you need to rely on international observations too. So we looked at that and we saw that we converted using this relationship. Next one, please. And GEM, the previous hazard maps, GEM conversion relationship was really biased, and the estimation of MW was really high. For example, if you have MB of 3.4 earthquake, you come up with MW 4.8, which is unacceptable. So we didn't use that, and we used our relationship for MB, and the value, the red line is showing our relationship for the MB case. And then ML is actually quite good. ML is the local magnitude. Usually networks report the local magnitudes, and we found a relationship with that. So the goal now is to push everything to MW. Next one. So if you put together all this, we come up with the how we did be compared to ISC. That's usually our basis to compare ourselves. Are we doing better than the international catalogs? So between 1900 and 1954, there is an annual rate of earthquakes are 7 compared to ISC in between 1900 and 1954. So that means 7 world earthquakes exceeding 5 and higher exist between 1954. This is very important information. In 1955 to 2003, there is 3 more times earthquake occur magnitude 5 and higher for the catalog between 1955 and 2003. This is all putting together this direct measurement. This is the middle one is us, because we measure directly the magnitude. The previous one is carefully examined using the other information, including Ambrosius et al. And if you go to modern era, we're still okay, we're still slightly better, but digital era magnitudes are much better than they were before. Next one. So we come up with the homogenized catalog after combining everything, finding the relationship, and so these intervals are important because it shows you which year ranges that I can record the magnitude, I can trust the magnitude I have in the catalog. Basically, if you look at 1980, year 1980, less than 4 is not well identified. That's the data showed us. So we kind of identified in the intervals that you don't include any event by mistake reported as 4 in your catalog that will affect your Gutenberg-Richter relationship. So how did I do the magnitude calculation? This is the technique we've been using, and it's actually now it's kind of exciting. It's becoming very widely used around the world, even with USGS, with other organizations. In Berkeley Seismology Lab, they are trying to adapt to calculate magnitudes faster for smaller events. And the method was developed in 1996 by my colleague, and I took it and developed a little further. The quality control of the data is based on amplitude difference. Basically, if you have an event occurring here, and if I'm close that much, and if you're there, you're losing the energy, so you need to identify how much this energy is lost, and you need to be determining this very well so that the magnitude is calculated robustly. So for this particular study, we used 300 reg MWs, and they were within the range of 3.2 to 6.9. Next one. Again, this figure, I wanted to show this, and we showed that at Seismological Society of America in April or May in Miami this year. So the Gutenberg-Richter relationship, basically, which contributes to the recurrence intervals, needs to be carefully, again, I am pressing this, needs to be carefully examined. Because if you make a little bit mistake, if your magnitudes are overestimated or underestimated, this curve changes, the B-value changes. And then the number of earthquakes and the homogenized NWs, because it depends on these values, the conversion relationship will be different. So that's the point I wanted to make with this. You'll get different lines, different angles, and that will affect your hazard maps. Next one. So I want to now shift gears towards what we have been doing and what are the next steps in terms of seismological development in the country. This is a really exciting map for me, because if you look at this, 5 years ago there were very few stations. So national network, the yellow ones, improved. It includes both good quality broadband and short period and strong motion stations. We also my program provided funds, about nearly $500,000 to NSF to match the funds to deploy 52 seismic stations in the region in the Caucasus. Next slide. And this is how it looks like now. So NSF and Seismic Cooperation Program through the Science and Technology Centers, we send funds through stations to be deployed in the region, but the equipment is actually a loan. You use it 3 years. It's called Iris Pascal system. So you use it for 3 years, 4 years, then you send it back. But during that time, the transect, you see this line is actually seismic stations. So that will tell us what is going on in the Caucasus, what's going on, the model development, the earthquake, the seismics, and everything. Next one. And this is how the deployment was done, even with the hardest conditions, with helicopters. And what is very exciting to us and new in the world, Pascal never had the deployment, had the real-time telemetric signal coming to the centers. That's happening first time in Georgia. And finally, I want to show this no seismic study is complete without GPS arrows shown. So this is GPS. It's a little bit complicated figure, but it's showing you something. What it is the shortening in Caucasus. You know, there's a certain tectonic progress going on here. But we always thought before the GPS, Anatolian Plateau is pushing from here, and then there is double zone, and there must be a lot of high velocity rate for the global positioning system. But we didn't see it. Actually, after GPS installation, so you basically put the GPS, monitor years and years. It was since 1994, some stations goes back. Actually, with Rob Rylinger, right? He started earlier studies. But then the new stations were deployed. So 94 till 2008, it's quite a year. So you can take the average of how much this point moved to the other point. So that kind of shows how the plates are moving around. Next one. this is the final slide. Well, actually, I have another one. This is the new and exciting project. Again, we had this workshop last week in Georgia. Georgia is the lead, and Thea is the project leader. She is going to work with Central Asia and Caucasus to now deploy a larger network in the region, and expected to be complete in 2020. Summary slide, please. Okay. I'll put this and I'll finish. So what we did, we were able to improve and increase the number of events in the catalog. Local large magnitude of events were missing, which impacts the hazard a lot. So one point I want to make, catalog development is an ongoing process. Even today, tomorrow, you have new events, new catalog, new regions maybe. You did one study, you found this fault, this one. So this is ongoing process. There is nothing like, I did this, it shouldn't be that, it shouldn't be this. No, there's going to be a new map different than this one. So we need to accept the fact that new science is proving something new, and then we wait for the next steps on science, and we take and adapt it. That's the point I'm trying to make here. Also, the exciting took for me personally, because this is like my personal project with Livermore, the Coda magnitude, we were able to calculate down to 3.2 MWs, which you ask anybody, it's actually a big deal for a large region like that. Normally, very small regions can calculate, do other type of analysis for magnitudes, moment magnitudes. So, I think other thing I feel, as a program, we feel very good about the training workshops that we did. And the last one, 2 IAS employees went to Canada and worked very intensively with tuna. And they ran PSHA, they learned quite a lot. And I feel like PSHA Ready Catalog, I'm going to emphasize again, has to be revisited periodically, whichever time interval you pick. Also, we believe, Tuna and I, the IAS of the Elias State University is now fully equipped to continue this study in the future. Thanks a lot. And if you have questions, let me know.
You have shown us the magnitude relation for GEM, global, but inside GEM there was also project ME, ASCII model for Middle East, and we were involved and prepared catalog also. Have you used this catalog first? And the second question is this relation for Caucasus obtained in ME is different, I think, from this global GEM. Yeah, okay.
I think the question is, did we use the GEM catalog? Is this the question? Is there a question that you ask if we use the GEM catalog? ME catalog? No. Why? Because ME catalog is built by the group of people that believe the locations were right, and I examined the catalog and I saw some parts need improvement. Our base is ISC, International Seismic Center, and the local network data. So other studies can do their own catalog. Any individual PSHA study can be independently building their own catalog. That's as much as I want to say at this point, okay?
You said that first in time in this project, low magnitude events were considered. What is the influence of this low magnitude on the hazard analysis?
Yes, good point. Do you want to respond to this?
First, a little clarification. First time we went down to 3.2 directly calculating moment magnitudes with no conversions needed. Because if we do need conversions, it biases the results. So we try to go as low as possible, directly calculating, estimating moment magnitudes. How low you go in a catalog, in a hazard assessment, how it impacts the hazard assessment is that slope of that curve. So we need to get the large magnitude earthquakes right, but we also need to get the small magnitude earthquakes right. Because if that slope is different, then you're estimating more or less than real number of large magnitude earthquakes in your hazard assessments. So it certainly has an impact.
Just some comments, because lately GEM published a new publication about correlation between different type of magnitude, and there are dozens of relationships, not only this that we see here. And directly 1 month ago in Switzerland, we are investigated all of them and their sensitivity, and also Institute of Geophysics also are investigated different type of magnitudes, and there was quite good correlation with some of them, and I have not seen here this correlation. So there was just some of them, not all of them. Just comments.
She's just commented that she's not seeing her magnitude relationship here, and it's not our job to bring other people's magnitude relationships. Yes. Yes. Okay, I understood. Okay. Yes. There are all kinds of relationships that I didn't show it here. I selected only 3. Okay. Yes, because I have it, but I cannot show like 12 relationships. It's when it is published, this is what I think the correct thing to do. It's publications, usually the peer reviewers, they look at your papers and they look at your results and the relationships, and they approve it, and it's published, and maybe that's the place to show. I didn't show everything on purpose because this is like a very short time. Sorry.
უკაცრავად მე ქართულად უნდა ვისაუბრო. იგor, მაგი პожалуйста. მომეხვდეთ. ესე იგი, თქვენ წინა ეკრანზე ნაჩვენები იყო, რომ როგორ გადაადგილდება საქართველოს დედამიწის ზედაპირი.
You showed in the previous slide how the territory of Georgia is deformed. GPS, using GPS, yes.
იქ თქვენ აჩვენეთ, რომ საქართველოს ტერიტორიაზე სხვადასხვა სიჩქარით მოძრაობს ზედაპირი, 3-10 მილიმეტრი.
It is shown diapason from 3 to 10 millimeters per year.
ამ დროს შემხედ ასებული ინფორმაციის შესაბამისად, აზერბაიჯანის შუა ზეგანის გადაადგილება შეადგენს 14 მილიმეტრზე მეტს წელიწადში.
And in Azerbaijan, as according to Johnny's information, the deformation is more, about 14 millimeters per year.
თუ გავიხსენებთ და შევადარებთ, რომ ირანის ზეგანი სეისმური თვალსაზრისით არის ძალიან აქტიური. მარტო 2003 წელს 15 წლის წინ მოხდა მიწისძვრა და 33000 ადამიანი დაიღუპათ. თორე 25 წლის მანძილზე 75000-ზე მეტი ადამიანი. ყოველ 2-3 წელიწადში ერთ მიწისძვრა არის მოსალოდნელი. თვითონ ირანის ზედაპირის გადაადგილება უფრო სწრაფია ვიდრე აზერბაიჯანის.
So in Iran, what is in Iran territory? What deformations? According to data, very many earthquakes occurred last years and many people died. So maybe deformation is more than here. In Iran, yes.
So I don't know, because I am not studying GPS in Iran. So I think that's something for publications. I know that there are publications about velocity, GPS, or how plates move. It's not my expertise here. It's not, yeah.
ქართულად ვიტყვი მაშინ რომ გასაგები იყოს მოკლედ რასაც რენგენი რასაც გვეუბნება ეს ირანის რაც თვითონ გაიგო რომ ირანის დეფორმაციის სიჩქარებს მე არ ვსწავლობ და ამიტომ არ ვიცი მაგრამ აქ როდესაც დეფორმაციის სიჩქარებს ვსწავლობთ კავკასიაში ან საერთოდ თქვათ აზერბაიჯანში და ასე შემდეგ კი დასავლეთიდან აღმოსავლეთისკენ ისრების სიგრძე ანუ გადაადგილების სიჩქარე რომელსაც წერტილში ვსვამთ გეოდეზიური აზომვების დროს რა თქმა უნდა იზრდება და ვარირებს მაგრამ ის რომ თქვათ თქვენ გაქვთ ძალიან დიდი ისრები ხომ ეს არ ნიშნავს რომ აუცილებლად მიწისძვრის სახით უნდა გამოიყოს ეს ენერგია ეს ძალიან პირდაპირ ანუ რა თქმა უნდა პირდაპირ დამოკიდებულება ამ ორ თქვათ მაჩვენებელს შორის არ არის თავარი აქ როგორც თქვათ გეოლოგები აღნიშნავდა გეოდეზისტები მე არც თქვათ ჩვენ ჯგუფი გეოდეზისტები აქ არიან და გეოლოგებიც აქ არიან აი ამერიკიდან არის ჩვენი კოლეგა რომელიც ამ საკითხზე მუშაობს აზერბაიჯანის საკითხზე ეს არის მასთან კითხვები და ამის შემდეგ ამ შეგვიძლია რომ მას ვკითხოთ იმიტომ რომ ზუსტად აზერბაიჯანის საკითხები აქვს მაგს გავლილი ამიტომ ხო ეს სხვა თემატიკა ამისგან განსხვავებით იმიტომ რომ მიწისძვრის სახით ხანდახან ხო ასეისმურად ხდება ხოლმე ენერგიის სხვა რაღაცები ხდება ეგ არის აი მაგისთვის გაკეთდა ზუსტად ეს ტრანსექტი პროექტი იმიტომ რომ შიგნით დავინახოთ რა ხდება მიწაში აი ეს თქვათ რაც ნახეთ თქვენ ამერიკული ქსელი რომელიც გაკეთდა 58 სატურე 72 წერტილზე ვაკეთებთ მთლიანად კავკასიაში დაკვირვება ზუსტად მაგის გამო ამიტომ რომ სხვა გეოლოგიური კი არის სხვა ტექტონიკური პროცესები მიმდინარეობს ვიდრე გვეგონა აქამდე ამიტომ აი ზუსტად ამიტომ ვსწავლობთ ამას და ძალიან საინტერესო კვლევები იქნება 3 წლის მერე ცოტა დაგველოდეთ იმიტომ რომ დღეს მასალას ვაგროვებთ და მაგრამ აი რაც შეეხება აი ამ თქვათ აღმოსავლეთის თქვათ დინამიკას აღმოსავლეთის ტექტონიკურ დინამიკას აი ადამი არის ძალიან მაგარი ვიღაცა მაგის იმიტომ რომ აზერბაიჯანში მას აკეთა კვლევა და მუშაობს ჩვენთან ერთად ცოტა აქვს ძალიან ცოტა აქვს კი მაგრამ რაჭა ამომხდარი რაჭაში 3 მეტრზე მეტი გადაადგილებები კი არ არის მაგრამ რაჭის მიწისძვრა ამომხდარი ამიტომ ასეთი პირდაპირ დინამიკა არ არსებობს ამაში სხვა რაღაცეებია მოდი ამაზე ვილაპარაკოთ ხო აი აუცილებლად ადამიანთან ერთად იმიტომ რომ ძალიან საინტერესო ადამიანები არიან აქ კვლევას ატარებენ
Okay I think we need to move to next part of the talk thanks very much for the great questions Tuna Onur is she's going to introduce herself, but she's been working on this project, and she is a consultant with Livermore, and we have other projects around other parts of the world, including Iraq and Central Asia. We completed maps of Iraq, and it's actually now being printed as a building code, seismic provisions of new building codes. So, here.
Thank you. Good morning. So, after all this hard work that Rengin presented, my pleasure and honor is to present to you what happened. What did we do with that information, with that data? What did we estimate in terms of hazard in Georgia with this new information that came to light? My name is Tuna Onur, and I'm a structural engineer specializing in earthquake risk. So I also serve on the National Building Code of Canada's Seismic Provisions Committee since 2009. In Canada, we change our code, update our code every 5 years. So we do a lot of work ongoing all the time in terms of building codes and how new information, new science that comes to light in terms of seismology gets transferred to engineering practice. What do we do with that science in terms of actually applied engineering and how do we design our structures and so on. I'm also an adjunct professor at University of Victoria. I teach earthquake engineering there and again address a lot of my role generally is to address seismic hazard and seismic risk. So I'll start immediately by the problem you have at hand right now. It's not a problem, actually. It's good news that you have a new building code coming up, and it's being worked on right now, and it's adaptation of the Eurocode. Now, Eurocode Eurocode is organized in a way that every country has a say in what kind of hazard maps and earthquake loading they use for their own country. So that's their own independent selection. But the structural part of Eurocode you must adapt as is if you are going to say you're following Eurocode. So parts of the code, the design concepts, the countries have to adopt as is, the engineering concepts. But the hazard maps and the seismic loads, you have flexibility to choose for your own country. I say this up front because I'm going to bring our hazard map results to this. So how do we tie from the hazard, understanding hazard, to moving it into the building code? So the current probabilistic hazard maps we're working on right now as part of the project Rengin described is more or less finalized, but we're doing some fine-tuning still. So they're very close to being publicly released. But you need, in this country, Georgians need to make 4 decisions based on the way these hazard maps will be presented for the purpose of the building code. And one of these decisions is return period of the hazard. So what kind of hazard levels, probability levels, and return periods you want to use for Georgia, for design in Georgia. And this is a conversation in terms of engineering and how the engineering piece will come into the building code, but it's also a societal conversation. What kind of risk do you want to take when it comes to building your structures in terms of earthquake risk? The second one is the site class for which these hazard maps will be prepared. So as all of you will appreciate, ground shaking is different on rock, very stiff rock, and it's different on soft soil. So these hazard maps are going to be given at a uniform site class for the entire country. Then the building code has tables to adjust these ground motions to various types of ground conditions. So that base level, that reference level needs to be decided by the building code. It's an input from the building code committee to us so that we could prepare the maps for the right ground conditions. The third is use of the full uniform hazard spectrum, and I'm going to show you the spectra so maybe you'll have a better sense of what's the spectrum and why it's important for engineering. But whether to use fixed shape spectrum versus the entire uniform hazard spectrum, because we're calculating these hazard values. I'm going to show you mainly peak acceleration values in the hazard maps, but really the engineering uses not those at all. It's the entire spectrum of spectral accelerations. So that decision is also key. And finally, the performance requirements. Again, this is partly an engineering, partly a societal decision. So what kind of performance do you require from your buildings in case of an earthquake? Would you like them to have extensive damage, bar collapse? So they can have a lot of damage, but they're not going to collapse and kill people. Is that the goal? Or is the goal that your buildings, after an earthquake, that the design level earthquake, are still have enough capacity that people could stay in them still? So there's actually this conversation needs to happen before you decide your load levels. Next one, please. So now I'm going to talk a little bit about the hazard maps themselves. So into the development hazard maps, this particular project went alternative source models and alternative ground motion models. The big thing to know about seismic hazard, really the most important thing to know, is we don't know. We don't know the exact answer. Science can give us the best possible estimate, but it's an estimate. Nobody knows the actual earthquake hazard. If they say they know exactly this is how it should be, don't believe them, because there is no such thing. We're still learning about earthquake catalogs. Earthquakes are occurring. We're improving our monitoring so we can record more and more earthquakes and understand the patterns of seismicity. We're also learning a lot more day by day about tectonics and active faulting and how much slip is happening on these faults, and long term, what kind of hazard we expect. So there's no right answer. What there is what's the best answer right now with what we have, the information that we have. So to capture that fact that we don't really know in this particular project, and also generally, the practice is to use various alternatives. So rather than just One, this is my judgment. You use many, many alternatives so that you are not biased by one piece of information or this piece of information. You're using all available information. So this we apply to both the source model side of it. So earthquake hazard is really two components. One is the earthquake occurrence itself, the faults, the earthquakes, the catalog. But the second piece is when the earthquake does happen, how much the ground shakes. That's also a different area of research, and that also we use alternate ground motion models. And for the source models, we use both the catalog, but that gives us a short-term, last 100 years, Rengin mentioned our recording history is fairly short. But the earthquakes have a lot longer return period than that. So we've been recording earthquakes since 1900 with instruments, but in many parts of your country, the earthquake recurrence itself could be as long as 2,000 years, but we don't have that long record of recorded earthquakes. So what do? We supplement the earthquake catalog by the long-term active faulting studies to understand the long-term slip in the area. So both of them has to go hand in hand. And in terms of the ground motion, I'm really, really excited about Rengin's announcement that there's all these new instruments are going in, but co-located with strong motion instruments particularly, because when a major earthquake happens, the one thing that we need as engineers, how much did the ground shake and did we do it right, is strong motion data. Weak motion data is great in locating earthquakes and calculating magnitudes, but when it comes to actual damage to the buildings, we need strong motion data. So the new network is also integrating strong motion instruments. But until we have a lot more data, we rely on latest global models combined with models that use local data as to the extent possible. So in terms of the seismic source characterization, I'm not going to go into too much detail. Rengin has really nicely presented to you what the new earthquake catalog represents. It has a lot of newly added local events for the territory of Georgia. This is incredibly important. New direct moment magnitude calculations. This is also incredibly important because as we were talking, if your magnitudes are biased, your hazard results are going to be biased. New region-specific magnitude conversions. We've looked at various conversions relationships. Rengin showed only a few as examples, but we found that with the new catalog, with all these new added events and the newly calculated, directly calculated moment magnitudes down to small magnitudes, we saw a lot of bias in the small magnitude end, which is not surprising because until this study, there were no moment magnitudes directly given for small magnitude events. This is the first time in your territory and in this region a moment magnitude 3.2 is being calculated directly from data. So it's not surprising. And extensive earthquake relocation work. So you saw Rengin when she showed the original catalog when the earthquakes fall on a grid. Earthquakes don't fall on any kind of mathematical pattern. So this relocation work really corrected that old biased catalogs, locations, accuracies incredibly improved in this new catalog. So this is wonderful for me because I'm not a seismologist, but I get this wonderful data set from my seismologist colleagues to work on in terms of calculating the hazard. And Georgia is blessed with many active fault studies already existing in the country, but there's also new efforts going on, so we incorporated work from Georgia, our US colleagues who are doing an extensive study right now in terms of tectonics in Georgia, and also Turkey. So our workshops incorporated these experts to come in to Georgia and discuss active tectonics in this country. So, in a snapshot, I have one slide for each. Here's the catalog that Rengin presented, and the fact that so if you look at the time periods here in 55 to 2003, we have double the number of magnitude 5 and higher earthquakes. Just think about that for a second. Magnitude 5 and higher earthquakes. These are very significant earthquakes that can cause damage in your territory. So the blue catalog is our catalog, and the red catalog is the global catalog. And in the 1900 to 1954 years period, we have quite a few, it's more than 10 times more of these damaging types earthquakes. Yes. And in terms of active faulting, again, as I mentioned, there's some really good work already existing in the area. This is one of them, Adamia and others study. So we've informed our decision making in terms of modeling earthquake hazard here with the existing studies, but also new studies. Next slide. This is the Eric Cowgill's group is now doing an extensive study of active faulting in the area with a lot of field work and estimating slip rates for these faults. So putting it all together, we came up with various alternative source models. I like to show a few examples here. And estimating the earthquake occurrence rate from observed earthquake rates. So in these two figures, on lower left corner of the slide and the upper right, you see in blue observed seismicity. So what's been observed so far in the catalog, and the red is the modeled seismicity. So we give it a maximum magnitude, we stop at that maximum magnitude, but you see how well the catalog is very clean. The blue lines perfectly align on a line. Maybe I should have shown a bad example because we don't have it in our study. Luckily, the catalog is so clean now that all these points are nicely aligned on that straight line. In poorer quality catalogs, you'd see those blue dots everywhere. They wouldn't nicely align like this. And the red is basically what we're estimating based on the existing, the actual observed data. And so up-to-date ground motion models as well is a key part of this. In fact, I'm going to go out on a limb and say the uncertainty in the ground motions is one of the things that impact most the outcome of your seismic hazard assessment, more so in many cases than your source characterization. These are the 5 relationships. The last 4 are global relationships that we use, and the top one is a relationship that uses Eastern Mediterranean and Middle Eastern data, so a little bit closer to your region. And the way we weigh these is what informs how we use these. Next slide. Is we basically compare them all at various magnitudes, various distances to locally recorded ground motion data. Unfortunately, that's very limited at the moment, but I'm very hopeful that in the future we'll have even more strong motion data to improve these, continue to improve these maps. So here's, with no further ado, so this is one example we have a suite of maps. It's not just one probability level, not one site class, not one period or one ground motion node. We have it for PGA, all the spectral accelerations, for 2% in 50 years, 10% in 50 years, various probabilities of exceedances, and also various site classes. So this one happens to be a 10% in 50 year. I'll start with this one because this is roughly what you could compare to your existing hazard maps in your building code. And it's for site class C, so this is a fairly soft kind of site class, but the reason why I chose to show this is because your existing hazard maps are on site class C. That's your reference in your existing current building code, that's your reference site class. So if you look at the map, you're going to see that in our map, and I'll show you yours as a reference next slide so that we can compare. But one of the things that jumped at me was how Batumi's hazard has come up. So that's one of the things. Tbilisi, fairly comparable to what you had before, maybe a little bit higher. And the other thing that's a little bit different is in your old map, you had a swath of the Caucasus showing fairly similar hazard, although that's also misleading. I'm going to show in a minute why. We see a little bit more pattern in the Caucasus. We see that a little bit less hazard in the west and a little bit more hazard in the east. And that's actually borne by geodesy as well. There's faster plate movement, as we were discussing, towards Azerbaijan than there is towards the west. So that's kind of consistent with the seismic hazard maps. So if we go to the next slide, that's your current map. Your current map is in terms of intensities, but it's very lucky that you also have acceleration contours on it as well. So I was able to compare a little bit. But I also note that because in your current map, your zoning is by intensity, the entire northern part of Georgia is shown in one color. But that's misleading. If you look at the actual contours in accelerations, you're going to notice that actually it's lower in the west and higher in the east. Again, it's consistent with what we see in the new hazard maps, and it's not surprising because, again, the plate's motion rate in the east is higher than the plate motion rate in the west. So it's all kind of internally consistent. So slip rates agree with seismic activity rates, and your old map actually didn't do a bad job of capturing that. The only thing is that you used only 3 categories for design. If you had zoned this map a little bit more in detail, maybe in the north you wouldn't have done a very bad job at all. But this map is missing the hazard in Batumi. 0.08 G is a very, very low acceleration, and our maps, if you flip back up to the previous map, in Batumi is going to show somewhere around 0.2, 0.3 G acceleration. So that's a major difference between your old maps and this map, is that there's a lot more hazard in southwest of your country than there was in your original maps. But I don't want to dwell too much on the differences for now. Let's keep going. So the one after that is, now we're going to go to a different site class. This is site class BC boundary. This is a stiffer soil now we're looking at. And the reason why I put this up here is most international maps are prepared for this reference condition. And I wanted to compare, because I saw the Batumi discrepancy between your old maps and your new maps. So I wanted to see what are the Turks doing over here, right? Because they just released a new national seismic hazard map for their building code. So I thought that would be interesting to look at. So to compare though, because they use this site class as a reference, I'm now plotting the same results for that site class. So let's first, can you go back? So here, now we're looking at, because the site class is stiffer, we're now looking at a lower ground motion. So again, in stiff sites, the ground shakes a little bit less than softer sites. So instead of 0.25 G, now we're looking at something like 0.2 G. Now if we go to the Turkish maps, the newly released Turkish maps, it's the same return period, 10% in 50 years. It's the same site class, 760 meters per second. The comparison is right there at the border, it's 0.15 G. So this is a fairly recent study too, so I think it's a fairly good comparison. We're slightly higher, but maybe that's not a bad thing. Okay, so next map, please. So those were 10% in 50-year maps. That means there's a 10% chance that when the actual earthquake happens, the ground shaking will be higher than what we're predicting in these maps. So I'd like you to think about that for a moment, because you are now deciding to put some hazard maps into your building code. Would you be happy as a society that 10% of the time, the actual ground shaking will be higher than what you put in your design maps? Is that acceptable? Or perhaps you need to take that risk a bit lower. In Canada and the US, we use 2% chance of exceedance in 50 years. That means that we consider acceptable that it exceeds the design, and the actual ground shaking exceeds the design level only with a 2% chance. 10% is too high a risk for us. So it's a decision for Georgia. It's not my judgment to make, but I wanted to show you what would the difference be if you did 2% instead of 10% chance of exceedance in 50 years. Well, let's look at the values. So this one is also for 760 meters per second. So if we can go 2 slides back. One more back. Okay, so for Tbilisi, for example, now let's focus on Tbilisi. For Tbilisi, we have about 0.2 G, a little more than 0.2 G, so 0.25 G, let's say. So let's go up. And for 2%, for Tbilisi, we have 0.4 G. Roughly, this is a rule of thumb, but it will vary by different regions. Roughly, the load goes up by 2, right? A factor of 2. So you're now designing double the load if you're designed to 2% in 50 years than you would in 10% in 50 years. Next one, please. And we'll see that also in, I wanted to show the engineers in the room some spectra, because this is a very powerful tool for engineers to understand which period structures shake how much. So just to give you a little bit of background on this for the rest of the audience, every building, depending on their material and height, they're going to have a natural period of vibration. Tall buildings vibrate with long periods, so slower vibration. Short buildings have a shorter period, so they vibrate faster. So that's important because when the earthquake motion hits, earthquake ground shaking, earthquake motion contains all kinds of periods in it. But your building feels the one that's closest to its own natural period of vibration. So short buildings will be more impacted by this part of the spectrum, and the tall buildings will be more impacted by this part of the spectrum. So it's a good tool for engineers to do design for various types of buildings, various natural periods of vibration buildings. Now again, if you look at the 10% and 50 years, so these are now by city. So the blue, the lowest one is Batumi, obviously. The middle one in the middle is Tbilisi, and the highest one is, and I'm going to pronounce this wrong, I'm sorry, Sink Valley. And so the 2% in 50 years is, again, like you saw on the map, is about roughly double the 10% in 50-year values. But these are the sort of spectra that can go straight into your building codes. So let's go to the next slide. So the 2% and 10%. So you'll sometimes also hear return periods of ground shaking when building codes are referred to. So 475-year shaking and 2,475-year shaking. So those are directly related to the 2% in 50 years and 10% in 50 years through Poisson distribution. So it's just a mathematical distribution that makes that connection between the return period and the probability of exceedance. Again, as I was alluding to earlier, choosing that probability level is important, and I'd like you to really understand what that means if you choose 10% in 50 years versus 2% in 50 years. You're really, in effect, choosing acceptable level of risk for your country. So it's not just a simple design decision, it's a societal risk acceptance decision. All right, so again, examples from Canada and the US, we both use 2% in 50 years for our design. A lot of countries in Europe use 10% in 50 years, including Turkey now switched to multiple probabilities of exceedances. So they don't use just one, they use 4 of them now. And my one point on this before I move on to site classes is think about what's more costly. First of all, doubling the ground shaking doesn't mean doubling the cost of the building. The design cost isn't necessarily scaled one-to-one with how much load, how much more the load is. So bear in mind that doubling load doesn't mean double the construction cost. But even if it did, can you afford building structures that will have a whole lot more damage in the case of an earthquake? Because think about it, if you have more damage, you're going to need more healthcare, more public housing, more reconstruction after an earthquake. In my opinion, if a country has limited resources, it's much better to design to the higher level, and every earthquake you have less damage, less destruction, less housing and healthcare and all the basic necessities of people who've lost their homes that your government has to deal with. So when you think cost, please think long-term cost, not just short-term construction cost. Okay, next one. And the reference site class I alluded to. So this is something that we need to have a conversation with your building code and see the new code, what the reference site conditions are, so the maps can be prepared appropriately for that site class. And the design spectrum decision. So instead of a fixed shape spectrum, in fact, US used to do fixed shape spectrum, they're changing it, so their new codes are also going to the full uniform hazard spectrum, and I highly recommend you go that way, because the fixed shape spectrum is really it's a relic of the times when us engineers weren't getting enough information from seismologists. They would give us only 0.2 second period acceleration and the 1 second period acceleration, and it was our way, of engineers' way, to come up with how that shape must look like in between. We don't need that anymore. Our hazard assessments have that entire, all the way to 10 seconds, we can give you hazard values. So I highly encourage to consider using the full uniform hazard spectrum for your new building codes. And so that's what it would look like. So instead of giving you hazard values at PGA, 0.2 second and 1 second, we'd be giving you the entire shape of the spectrum, not just the 2 points on the spectrum. And finally, performance requirements. So this is maybe a little bit ahead of time talking about this, but most building codes around the world design for life safety. Life safety means, so that performance levels in the building code means, the only thing you're achieving when you design your structure to the building code is that you will escape that building alive after an earthquake. It does not guarantee minimal damage. It does not control the amount of damage. You can have a lot of damage, but no collapse, and that's success in terms of building codes. Now, you need to, as a society, think, is this enough for us? In the world, currently, that's the norm, yes, but more and more countries around the world are debating this. The fact that my structure hasn't collapsed, but I can't go into it, I need to tear it down, I can't even repair it, I need to tear it down and rebuild is not success anymore. So more and more this conversation is happening around the world. US is moving in this direction, New Zealand is moving in this direction, and in Canada, for our 2020 code, because our last one was released in 2015, so we're in a 5-year cycle. Every 5 years we update our code. We're considering to go to a different performance level as well. We no longer consider it's enough that it hasn't collapsed. We need a bit more expectation from the performance of our buildings, in our opinion. And Georgia is actually in a very good crossroads right now, because you have the power to decide now for your new building code. There's now, I think in the US, 2 performance criteria, but in Canada, what we want to move is, so instead of, if 2020, if it goes ahead, what's going to happen is, from collapse prevention and life safety, which is your building is completely damaged, nobody can go in, it'll be a red tag building. After an event, you're not allowed to go in, and most likely it needs to be torn down and rebuilt, to this. We want to go in Canada for all of our buildings to immediate occupancy. So basically, it may not have your electricity or your facilities, it may have slight damage, but you can stay in it. So that's our goal right now. And I should mention, in building codes around the world, we have importance categories in building codes. So your homes are in this performance level usually, but your post-disaster buildings that are essential to function after an earthquake are usually in this performance category. So we already have this performance category in our building codes for post-disaster critical buildings. So what we're trying to do in Canada is to put all our buildings here and our post-disaster buildings here, which are already there. So I'm going to leave you with this thought. Thank you very much for your attention, and if you have any questions, I'd be happy to answer.
Thank you very much for nice presentation. I have just one comment and then many questions. So my comment is, you have compared the new probabilistic seismic hazard map with the old in terms of PGA estimation, and told us that that old map was not so bad. I'm really very surprised, because the new map is 10% probability of accidents and the old map is 2% probability of accident. So we cannot compare these maps. There are different levels, and when we compare 10% and when we have higher value in 10% probability of than in 2% probability, it means that the old estimation was just wrong.
Yes, no, you're absolutely right. I wasn't really comparing directly the values.
Yes.
I was comparing the fact that relatively in the West, less hazard versus in the East. That's all. I wasn't comparing directly the values.
Yes. And new estimations, there are very big differences, because in 2% probability, PLC was 0.60, now we have 0.24. That is less than that was obtained in EMA project. The minimum values there are 0.28. But this was regional estimation, and there was a recommendation to national estimation, and in national estimation we have a bit higher value. So there are differences. This is a comment, and now answer is possible. What type of declustering methods have been used? Declustering methods.
Okay, so declustering, we looked at various declustering methods.
Which
one
one?
that is used in the US, for example, is a very restrictive declustering method. It gets rid of about 2/3 of the catalog. We found that a little bit too much getting rid of earthquakes, because you can make hazard maps for many purposes. Here, by declustering, what we're doing is adhering to the Poisson distribution. It's a mathematical problem. What we feel is that because these hazard maps are specifically prepared for the building code, which means we're trying to assess damage from earthquakes, right? So we are trying to stop our buildings to get damaged from earthquakes. We feel that if you very heavily decluster your catalog and you remove earthquakes that are 5, 5.5, just because they're aftershocks, you're actually underestimating the hazard slightly. So what we did was try one that is more intermediate declustering than what the US does, and one no declustering. The results are actually not that different. So in this case, declustering doesn't really change the slope of the curve very much. So the results I'm showing have no declustering, but the ones that are declustered aren't making a huge difference.
Okay, actually there are very many, okay. And the second, I have not seen the map according to active faults, metadata about section segments, about slip rates, what slip rates have been used for this active faults.
So I didn't put a whole lot of technical details here, but it's going to be published when we publish it.
You are going to publish
Yes.
now?
Yes.
Okay, so this...
Both the catalog and separately the hazard maps.
Okay, so there are new estimation of slip rates?
There are some new estimations and some existing estimations. Some are consistent with older studies, some aren't, so there will be a mix. Yeah.
Okay, and I also have, according to these GMP models,
yes.
There are lately, there have been published new GMP models. How are you selected them? How are you selected all this model, and why are not used the latest GMP models for regional?
Our decision making was mainly on what ground motions are appropriate for Georgian territory. We did not follow necessarily what GEM did.
Actually, all of them should be checked, and then
yes.
should be. Okay. Okay, thank you very much. And also, many types of seismic sources have not been used.
I'm sorry?
Many types of seismic sources are...
That's right. We have alternate source zones,
okay.
Yes. Alternate source zones are great because if you give a seismic pattern to 3 different seismologists, you're going to come up with 3 different zoning schemes. So it introduces bias a little bit. So our way of getting rid of that was to use alternate source zones so that it gives a bit more objective result in the end, I think. Yes.
ბატონთა თქვენი დახმარება დამჭირდება უკაცრავად წინასწარ მადლობას მოგახსენებთ. წარმოდგენილი იყო ბეტა მრუდები. ბეტა მრუდებთან დაკავშირებით გვაქვს ძალიან ბევრი კითხვები. საქმე იმაშია, რომ ბეტა სპექტრის მოდრები ხო? სპექტრის. ეს. როცა ჩვენ მე მინდა მოვიყვანო სამუშაო სამეცნიერო კვლევითი მაგალითები, რომელიც ჩაატარეს ჩვენმა კოლეგებმა უკრაინაში ამასთან დაკავშირებით. სპექტრი. როცა საუბარი მიდის მაღლივ მშენებლობებზე, აუცილებელია სპექტრალური ანალიზის გაკეთება გრუნტის. სპექტრალური ანალიზი კეთდება როგორც წესი, სანამ შენობა დაიწყებოდეს. უკრაინული კვლევების თანახმად გამოვიდა შემდეგი სიტუაცია. გაკეთდა სპექტრალური ანალიზი ვიანგარიშეთ შენობა და შენობა აშენდა. მიწისძვრას ველოდებით, როცა შენობა აშენებულია. ახლად გაკეთებულმა სპექტრალურმა ანალიზმა უკრაინაში აშენებული შენობის ქვემოთ სხვადასხვა გრუნტისათვის მოგვცა განსხვავება 1.5-დან 5 ჯერ. თუ გაქვთ თქვენ მსგავსი, თუ გვაქვთ თქვენ ამაზე სტატიებიც არის გამოქვეყნებული და უკრაინულ ნორმებში შეიტანეს, ახალ ნორმებში უკრაინელებმა. გაქვთ თუ არა თქვენ მსგავსი გამოცდილება და რას გვირჩევთ? ჩვენ როგორ მოვიცეთ? გმადლობთ. 1.5-დან 5 ჯერ არის სხვაობა ძალებში. დიახ, სხვადასხვა გრუნტის მახასიათებლებისათვის. უზარმაზარი განსხვავება. ისე იგი შენობა სულ განსხვავებულად მუშაობთ, ვიდრე ჩვენ ადრე თვლიდით. თელის გათვლები, რასაც ადრე ვაკეთებდით, ადრეულნური არც ერთი არ იყო სწორი ფაქტიურად.
Absolutely, you're absolutely right. Side classes are critical. In this
თქვენ
study,
ძალიან მართალი ხართ. თქვენ აბსოლუტურად მართალი ხართ. გრუნტის ტიპები, ანუ side class-ი ძალიან მნიშვნელოვანი არის განსხვავება.
In this study, it's all for reference class because your building code will adjust it.
ეს ყველაფერი, თქვენ აი ეს კვლევა რაც გავაკეთეთ, თქვა აქ ხომ, არის დაფუძნებული ერთ რეფერენს გრუნტზე. ანუ თქვათ I don't know what reference class counts in Georgia. Hard in Georgia, the reference class. Yeah.
But I will share my experience from Canada.
მაგრამ მე თქვენ გაგზიარებთ აი ამ გრუნტის თვისებების შესახებ, გრუნტის კლასის კლასიფიკაციის შესახებ, ჩემს გამოცდილებას, რაც მაქვს კანადურ გამოცდილებას.
Our reference class is site C, so somewhere in the middle of the site class.
ჩვენი ეტალონი გრუნტი, ჩვენი ეტალონი გრუნტი კანადის შემთხვევაში ეს არის C კლასის ტიპის გრუნტი.
450 meters per second.
რომლის განტალღის სიჩქარე არის 450 მეტრი წამში.
We have amplification factors that are 4.5.
და ჩვენ გვაქვს გამადიდებლობა ფაქტორი 4 და 5.
For site class E, the softest site class.
გრუნტის ტიპისათვის ეტალონი გრუნტის ტიპისათვის E კლასის.
And the shear wave velocity is less than 180 meters per second.
და მისი ამ კლასის E კლასის გამტალღის სიჩქარე არის
180.
180 მეტრი წამში.
Now that is if the reference shaking is low. So it's like a 0.1 G.
და ეს არის იმ შემთხვევებისთვის, როდესაც თქვათ აი ეტალონი გრუნტის მაქსიმალური აჩქარება არის დაბალი 0.1 G.
When the reference shaking is high, they don't amplify that much anymore because it's already a high ground motion and there's nonlinearity in the side amplification factors.
I have translated correctly. So
when the reference shaking is high,
და როდესაც თქვათ ეტალონური აჩქარება არის დიდი, reference shaking,
so side class C shaking.
მაგალითად თქვათ ამ შემთხვევაში, მის შემთხვევაში ეს C კლასი
is 0.4, 0.5 G.
და როდესაც გვაქვს მაგალითად 0.4 G, ან 0.5 G აჩქარება.
The amplification is not very high. It's
მაშინ გამადიდებლობა, ანუ გრუნტის ამპლიფიკაცია არ არის დიდი.
Because there's nonlinearity.
იმიტომ რომ გვაქვს არაწფრივობა გრუნტის თვისებებში.
So for low levels of shaking, yes, we have 4.5 times the amplification between side class C and E.
მაგრამ როდესაც დაბალი აჩქარებები არისო, ხო, ასეთ შემთხვევაში გრუნტი განსხვავებულად იქცებაო. ანუ ერთი კლასის გრუნტი შედარებით განსხვავებულად იქცება, ვიდრე მეორე კლასის გრუნტი. ეს კანადური გამოცდილებაა.
But I'd like to say that it's not part of the study at all.
მაგრამ ეს ამ შემთხვევაში, როდესაც ჰაზარდს გაძლევთ ის, თქვათ ჩვენ სამშობლო ჯგუფი, ეს არ არის ამ კვლევის ნაწილი. ამიტომ გრუნტის თვისებები უკვე სხვა რაღაცა, სხვა კლასი არის უკვე, ხო. ეს არის რეფერენს გრუნტებზე, ეს გრუნტის თვისებები და მით კლასიფიკაცია უკვე სხვა სამუშაოა და ეს არის, რასაც აუცილებლად გავაკეთებთ მომავალში, იმიტომ რომ ამ ქალაქს ეს სჭირდება. აქავართ, ჯერ არ ჩერდებით, არ ვიცი, ესენი უფრო მაგრებიანია მაგალითად.
I can point you to recent studies that we're using for our national building code.
აი მაგალითად მე გეტყვითო მაგალითად აი ბოლო კვლევებსო რომლებიც თქვათ გაკეთებული ამ კუთხითო და თქვათ გაიცანით ამ კვლევებსო, იმიტომ რომ ჩვენ ამ კვლევებით სარგებლობთო. აი იცით რა არის მე ყველას მიდაგვრჩენ სამშაბათი ჯგუფები რომ აუცილებელია თქვათ გაიცნონ ამ შედეგებს დეტალურად. ტუნა ერთი კვირის განმავლობაში, თქვათ მომავალი კვირიდან არის აქ სპეციალურად რჩება ამისთვის, რომ თქვათ ცალკეულ ჯგუფებთან კონდეს და თქვენ ჩავნიშნავთ შეხვედრებს და აუცილებლად დეტალურად გავლით ყველა თქვათ იმ რეკომენდაციას, რასაც ის გვაძლევს, იმიტომ For the engineers, we have to direct our research towards that point because it's very important for us.
I'll also say this. These days, so for example, in the 2020 Canadian Code, we're switching to no reference conditions anymore. We're going to give you the spectra, the engineers the spectra for every site class. You don't need factors.
აი ახლა უკვე კანადის თქვათ სამშენებლო ნორმების კომისია მივიდა იმ დასკვნამდე, რომ უკვე თქვათ რეფერენს კლასებს აღარ გავცემთო. იმიტომ რომ სამუშაო გვაჩვენა რომ თქვენ რეკომენდაციები უნდა მოგცეთ თითოეული საიტ კლასისთვის, ASP-ისო, BEST-ისო.
And this study can do that for you too. So that could be part of our study.
ეს უკვე თქვენ მოგეხმარებათ. ჩვენ რომ თქვათ აქ რა გარკვეულ შედეგებდა ბიბლიო, შენ უკვე ამ სოდრის აპლიკაცია ჩვენთანაც შეიძლება რომ დავნერგოთ.
So each of your spectra will be directly from hazard assessment.
და ყველა ეს თქვათ სპექტრი უკვე პირდაპირ სეისმური საშიშროების შეფასებიდან Yeah, so he's showing that study from Ukraine. I ამას ამბობს, რომ თქვა გრუნტი სხვადასხვანაირად იცვლება, იქცევა სხვა ჩქარებებზე და დაბალ ჩქარებებზე კონტაქტს. Yeah, thank you.
Sorry. I have a non-technical question and out of scope of our today's meeting, but probably there are studies regarding what's the economic impact of having 2% probability and 10% probability, and between those classes, which was on the last slide, different levels of. If you can cite any work for us, it's not a matter of today's discussion, but this is directly related to what we will need to discuss when making decisions. So it will be very helpful for us.
Okay, so first question. I'm going to answer your second one first. So site classes doesn't matter, because one way or the other, you're going to adjust for site classes anyway. If we give you the hazard maps with what site class doesn't matter for, there's no economic impact whatsoever and there's no design impact. In fact, as I was mentioning, with our model is in place. Right now is the time to request these things from us. We can give the hazard values at all site classes if you like. It's a possibility, and your engineers can get rid of site class problem altogether. It can come directly from hazard, and it has no economic impact. The economic impact is going from 10% to 2%. And that's, in the short-term cost, yes, it's going to increase your construction cost. But in the long term, think, after an earthquake, do you want to be able to repair your buildings, or do you want to tear them down and rebuild and house a whole lot more people and provide healthcare and provide shelter and basic necessities? In Canada, we're currently doing a pilot study with an authority called BC Housing. So what they do is they provide shelter for vulnerable populations out of disaster times, just regularly. They now want they did an economic analysis, and they realized quickly that actually it's cheaper to build to the higher level and not worry about finding housing after a disaster for this many people. So we're doing a pilot study with our building code and the BC Housing Authority, where we're going to show clearly the economic advantages of building to 2% in 50 years and not worrying about, and in fact, not just 2% in 50 years, but also immediate occupancy. So that they don't need to find housing and more people are hurt and injured. So I would say long term, 2% in 50 years would be the cheaper option. Short term, for construction industry, it's going to be shock to absorb. But I'll say this too, it's going to be a shock no matter what. Their practices are going to change. The new building code has features that they've never seen before. So it's a wholesale change for your engineering community as it is. If you wait now and do 10% in 50 years and say, well, we'll do 2% later, it's going to be a lot harder. So this is actually a very critical turning point for you in your country, because you have such a big overhaul of your building code anyways. Incorporating this, yes, in the beginning there will be a lot of construction industry costs, short-term cost considerations, but talk to your civil defense people, talk to your emergency response people. They're going to be very happy that after a disaster, it will be a lot more manageable what kind of damage and destruction happens. Of course, all of this applies only to your newly constructed buildings, but Georgia is in a huge economic boom right now in terms of construction. I see construction everywhere in Tbilisi. I saw a lot in Batumi as well. So this is going to have an impact on how you design your buildings, but I think to the better. So my recommendation would be 2% in 50 years. I realize it's a big difference, but I think long term you're going to save costs for your country generally. But if you go 10% in 50 years, you're only going to save costs for your construction industry, not the rest of your government.
Thank you.
მოგეცალმებით, არ ვიცი ეგ თავდება თუ იწლება კამათი ამის თაობაზე, მაგრამ კი ბატონო, თავამთავი. ამიტომ კი ბატონო, მე თვითონ ვიტყვი. ძალიან სასიამოვნოა, რომ ასეთი მაღალი რანგის, ესე იგი, სპეციალისტები ესწრებიან ამ დათმის. თვითონ ეს გრანტი რასაკვირველია იმსახურებს უმაღლეს შეფასება. ძალიან კარგი ინფორმაცია. მაგრამ მე მინდა ხაზი გაუსვა იმას, რომ ესე ძალიან კარგია, რომ მინისტრების დონეზე ესე ხდება იმის შეფასება, თუ რამდენად რთულია სეისმიკასთან დაკავშირებით კაცობრიობის მოქმედება საერთოდ. აქ არის თქვენ ნახეთ რამდენი სირთულეებია ქვემოთ, თუ დავადგინოთ ესე იგი რა ხდება დედამიწის ქვემოთ, არა? ეს ერთი პასუხისგებლობა, იცით რა არის? აი ყველაფერი ამის მერე დამთავრებული დოკუმენტი მოდის მშენებლებთან. აი მშენებლებს თავის პასუხისგებლობა აქვს ესე. ეს ამბავი როგორ გამოიყენა? ეს არის ურთულესი ამბავი, ეს არის ეკონომიკასთან დაკავშირებული, ეს არის ეჭვებთან დაკავშირებული. ნუ გონიათ რომ ყველაფერი ისია, როგორც ამბობენ მეცნიერები. შეიძლება სულ სხვანაირადაც არის, არა და ამას იტყვიან მეცნიერები. მაგრამ დღეს ესე იგი ქართულ საზოგადოებას აქვს ძალიან კონკრეტული აღმოცანა. 15 წელიწადია რომ ამბობთ ესე თუ 18, რომ გადავდივართ ევროპისკენ, არა და ევროპული ნორმები ესე იგი ვერ ავითვისეთ, არა. ძალიან კონკრეტულად გვეუბნება ევროპა. მოგვეცით რუკა 500-წლიანი განმეორებობის 100-წლიანი განმეორებობა. აი ამაზე ახლა საუბარი, იცით? თორე ჩვენ ვიცით იქ რა ამბები ხდება, რა სირთულეებია. ამიტომ ესე იგი ამ სეისმოლოგებს ესე იგი თხოვენ კიდევაც აი ამ სამინისტროს დონეზე, ეკონომიკის სამინისტროს ორი პარამეტრი პირდაპირ წერია. ეს არის ეროვნული, ისეთი რომ ევროპაში ნორმები ერთიანია, მაგრამ არის ეროვნული დანართი, არა? თქვენ თვითონ უნდა გადაწყვეტოთ ესე. აი ორი პარამეტრი გვინდა რა, რუკა 500-წლიანი განმეორებობის და ესე იგი 100-წლიანი განმეორებობა. ეს გვინდა ჩვენ იმისათვის, რომ მე წავიწოთ წინა. რა უყოთ მე ამას, არა? ეს რამდენად განსხვავდება ჩვენ თბილისში ახლა ვანგარიშოთ მაგალითად დოლორჟეზე, არა? თქვენ რო გვითხრათ, რომ მოლოთხზე უნდა იანგარიშოთ, ეს საშინელება. თქვენ რო გვითხრათ, რომ მოლერცზე უნდა იანგარიშოთ, ესეც საშინელება. აბა რა ვქნათ? აი ესეთი რთული საკითხებია და ეს ძალიან კარგია, რომ პირველი ის მოვისმენთ და ამაზე რასაკვირველი თანხმიერები გადაწყვეტება და უმაღლეს დონეზე ყველაფერი იქნება შეფასებული. დიდი მადლობა.
ძალიან დიდი მადლობა.
დიდი მადლობა მინდა მოუხადოთ ჩვენ სტუმრებს. So just to thank you very much for this interesting presentation, and we are finishing this presentation, but I encourage very much our colleagues to have informal discussions, and that's the whole idea, I believe. Yes, so ჩვენი სტუმრები ერთი კვირით არიან და ყველა მნიშვნელოვანი შეხვედრა დისკუსია რაც დაგაინტერესებთ, შეძლებთ უშუალო კონტაქტში დამატებით გაარკვიოთ. დიდი მადლობა მოგზაურობისთვის.